subject was beautifully packaged by Isaac Newton in his three famous laws of motion. Which I'll summarize first for you. Newton's first law says that an object at rest will remain at rest, and an object that's moving will keep on moving with the same velocity, same speed, same direction, unless acted on by some force. Let's see, did I get that right? An object at rest will remain at rest, and an object in motion will remain in motion with the same velocity, both magnitude and direction, unless it's acted upon by some force. We call this the law of inertia. And what it says is that a natural tendency of everything is to keep on going. With the special case that if it happens to be at rest, to keep on being at rest, zero velocity. Natural tendency everything's natural tendency is to keep moving. And if it doesn't keep moving at constant velocity, in other words, if it accelerates or decelerates, then you've got some fast talking to do. You've got to explain that because there must be some force acting on it to change its velocity. The Greeks believed, by the way, to the contrary, that the natural tendency of every object is to come to rest. At least when I say the Greeks, I suppose we're really talking about Aristotle here, but most of the Greeks, or the Greek tradition at least, is that the natural tendency of an object, its natural state, is the state of rest, and every object has to come to its natural state of rest unless you do something different. That was the Greek notion, and it must be conceded that that's much closer to our experience in everyday life, right? If I take this brick here and give it a shove, pretty soon it comes to a stop. It does not just keep on going the way Newton's first law says. It comes to a stop just the way that the Greeks would have said. The Greeks would have said that's perfectly natural. It's the natural tendency of everything to come to rest, and you just saw it happening before your very eyes. Galileo realized that the reason this brick comes to rest is not because some natural tendency to come to rest. Its natural tendency would have been to keep on going, but because this brick precisely did have a force acting on it. In fact, almost everything in everyday life has a force of friction acting on it, and it's friction, not some natural tendency, that brings things to rest. force of friction, so the Greeks said it's the natural tendency of things to come to rest. I don't need to explain why that brick comes to rest. That's just what bricks like to do. Galileo realized that actually the reason this brick comes to rest is because there's a force acting on it, the force of friction. So the first law simply doesn't apply. That's why it doesn't keep on going. If you could get rid of all the friction acting on that brick, which is tough to do in everyday life because virtually everything has friction acting on it. If you could get rid of that friction, then you would see Newton's first law, the law of inertia, acting the way it ought to. The objects in motion would continue at motion. In the time of the Greeks, or even the time of Galileo and Newton, it was not possible to have a truly frictionless motion. We can do a pretty good approximation here with the air track. I hope you fiddle with these things. You know what's happening. I'm going to pump air from a reverse vacuum cleaner here, and there are little holes here, so jets of air come out, and this cart then will ride on a cushion of air, and it's pretty damn frictionless. Right now, there's a ton of friction in there, obviously, but when I turn this on, now,
Oh, I'm sorry.
I love that. That, folks, is natural motion. We don't often see it, but there it is. It's almost completely frictionless. And the thing just, of course, in reverse direction when it gets to the end. But so, I've often thought, you know, if Aristotle could have seen what you just saw, physics would have been advanced by about 1,500 years in that 10 seconds that it took to do that. Because Aristotle basically held back the development of physics by saying that things' natural tendency is to come to rest. Actually, that's not true. The natural tendency of things is to keep on moving. The trouble is that almost everything is contaminated by friction in everyday life. And that leads us, it completely misleads us. All of serious physics begins with Newton's first law of motion, the realization that it's not the natural tendency of things to come to rest, it's the natural tendency of things to keep on moving at constant velocity unless you do something, apply some force, that makes them do otherwise. In the time of Newton and Galileo, the only place where you could witness frictionless motion, think about it, the only place that these guys had access to frictionless motion was up in the sky. Planetary motion is genuine frictionless motion, and it's no accident that the history of physics depended crucially on study of the planets. It always seemed to be kind of bizarre, you know, why were these guys worrying about the planets and stuff? What's that got to do with physics in this room? The planetary system was the air track of Newton and Galileo. It was the place that they had access to uncontaminated motion, motion uncontaminated by friction. And as I say, it's no accident that that's where the laws of physics emerged from, was from studying motions of planetary objects because they're essentially frictionless. Okay, so the first law says an object will continue at rest or continue in motion with the same velocity unless you apply a force to it. The second law picks up where the first one leaves off. What if you do apply a force to it? If you apply a force to an object, then its state of motion, its velocity is going to change. In other words, it will accelerate. Force cause acceleration. If you do apply a force to an object, it will accelerate. How much do you reckon that object is going to accelerate?
Force divided by the mass.
Well, you happen to know the answer. Certainly is going to be proportional to force, right? If I applied the same force to a ping pong ball and to a car, I would expect a ping pong ball to accelerate a whole lot more. I'm sorry, I said it backwards. That's the dependence on mass. If I apply twice the force, I should get twice the acceleration. So the acceleration is certainly going to be proportional to the force. That seems reasonable. It's going to be inversely proportional to the mass of the object, how much stuff there is there. A really massive object, it's hard to get it going. So the second law of motion says that the acceleration is in fact proportional to the force applied and inversely proportional to the mass of the object. This, folks, is the logical way of writing Newton's second law. A equals F over m. Why do I say logical? Well, typically you're given the force, you know the mass of the object, and what you're trying to calculate is the acceleration. So that does it for you. A equals F over m. For some reason, I guess because textbook authors are nervous about writing fractions or something like that, nobody writes this in the logical way. Instead, they multiply the m through and twist the whole thing around so that it reads F equals ma, as though what you were trying to do was calculate the force and you knew the mass and the acceleration. That's very rarely the situation. So this is logically backwards, but it says, of course, exactly the same thing, and it's an easy way to remember it, perhaps. That's in one dimension. In 3 dimensions or 2 dimensions, force is a vector. Force can be applied in various different directions, and acceleration we already know is a vector. So in 2 or 3 dimensions, I would write this as a vector equation. F equals F the vector equals mass times A, the acceleration. Now let me talk about the terms that go in there. Mass. What is it? It's a measure of the amount of stuff in something. Actually, I'd like to say it's just a count, really, in a way, of the number of atoms in it. But that's not quite right because of big atoms and little atoms. So, but it's a measure of the amount of stuff. It's measured in kilograms. For which the abbreviation is kg. 1 kilogram. Got the idea? Half of that, half a kilogram. So there's mass. Force. What is force? That's a push or a pull on something. I'm being very informal, intentionally informal with these definitions. But force, because I think that these are primitive notions in physics. Mass, force, primitive notions that in a way are almost beyond definition. They're the starting point. But a push or pull on something. The one thing I would say about force, maybe this is premature, but in a course like this, I find that students start telling me about forces that are completely mythical, you know. A force, if I say that some force is acting on something, I want to see the guy's fist there, or the chain that's pulling on it, or something like that. Now, it's true that there are some cases like gravity where the force is, I can't see the chain that's pulling 2 objects together by the force of gravity. And friction, it's a little bit unclear exactly how the 2 surfaces are grabbing onto each other. But a force is an honest-to-God push or pull. And if you say that there's a force acting on something, I want to know exactly what's the nature of that force. We're going to talk about that more in a moment. Force is a push or pull on something. It's measured in newtons, for which the abbreviation is just capital N. How big is a newton? Well, I've got here a newton meter, a Newton measuring device, and we'll see. 6 newtons, 12 newtons, 20 newtons, my little finger. Got the idea? That's about how big a newton is. 1 newton, not a whole lot. There's newtons. Now we know how to measure force. If you applied a force of 1 newton to a mass of 1 kilogram, you would get an acceleration of 1 meter per second squared. Evidently, one newton is equal to 1 kilogram meter per second squared. So actually, we don't need the unit newton at all. Instead of writing newtons on here, which actually they did, although it's kind of small, they could have written kilogram meters per second squared on there, and it would have said exactly the same thing, but kilogram meters per second squared is kind of a mouthful, so it's handy to have a shorthand for that unit. All I wanted to emphasize is that we're not introducing some new, fundamentally new quantity here. It's a derived quantity, the Newton kilogram meter per second squared. So, in a certain sense, the first law is a special case of the second law. I don't know if you ever thought about this, but the second law, in the special case where F is equal to 0, would say the acceleration is 0. If there's no force acting, then the acceleration is 0, which is to say that the velocity is a constant. That's exactly what the first law says. So in a certain sense, there's a much deeper sense in which this is not true at all, but on a superficial level, the first law is a special case of the second law. It's the special case where the force happens to be 0, and therefore the acceleration is equal to 0. What Newton's second law tells us is that force produces acceleration. Aristotle thought force produces velocity. But the first law tells us nothing required to produce velocity. Velocity is sustained naturally. That's what things naturally do. It just keep going at the same velocity. You don't need any force to keep something going at a constant velocity. A force produces acceleration, change of velocity. Nothing is required to sustain a given velocity. Okay, the third law says that if object A exerts a force on object B, then object B exerts an equal and opposite force on object A. What do I mean by opposite? Opposite direction, of course. This always bothered me. Equal and opposite. Well, either it's equal or it's opposite. It can't possibly be both. What this means in the fine print is equal in magnitude and opposite in direction. So, if A exerts a force on B, then B exerts an equal and opposite force on A. Here's an example. We've got two people, and they've got a piece of rope between them, and they're both pulling. So, here's object A and object B. And they're pulling hard on the rope. Imagine they're pulling hard on the rope here. Then A is exerting a force on B, and it's over to the left, right? F, that's A on B. A is pulling B over to the left. What the third law says is that in that case, B is pulling A over to the right, and the force is exactly the same. If A A exerts a force on B, then B exerts an equal and opposite force back on A. In letters, I could write F B on A equals minus F A on B. Like that. We're going to come back and talk about the third law next week. But for now, let me just mention one thing. The third law is a very slippery law. It's very easy to misuse the third law. Most of the misuse and wind up with absolutely absurd conclusions. You'll see some examples later on. Most of the misuses of the third law, in my experience, involve two forces that are acting on the same object. Two forces acting on the same object, Newton's third law doesn't have anything to say about that problem. Why? Because the two forces in question here, by nature of the third law, always act on two different objects. One of them is a force on A, the other one is a force on B. If you've got two forces that are both acting on A, then Newton's third law simply has nothing to say about the subject. But it's very easy to slip into a misreading of this of Newton's third law. So, note, I'll just put a note here for future reference. Two forces act on different objects. So if you're ever wondering whether you're correctly applying Newton's third law, one quick test is look at the forces you're talking about. Are those two acting on the same object? In that case, Newton's third law can't possibly have anything to say about this. So there are the three laws of dynamics, Newton's three laws of motion. Object at rest keeps going. Object at rest stays at rest. Object moving keeps going in the same velocity. F equals ma tells you what happens if you apply a force to an object. And the third law says force of A on B is equal and opposite to the force of B on A. Did I say that backwards? A on B is equal and opposite to B on A. Now, there are many different physical agencies that can produce forces, exert forces on things. And in a way, what I'm going to be doing for the next couple of lectures is assembling a catalog of kinds of forces and running a string of examples and applications. Basically, using the second law, F equals ma, which is by any measure the most important law in all of physics. F equals ma. So, kinds of forces. Weight. An object in free fall, we know, accelerates with an acceleration g. So here it is. It is accelerating downward with an acceleration g. Evidently, there must be a force on it. If it's accelerating, that's what Newton's second law says. F equals ma. Apparently, there must be a force on it. A force on it in the amount, well, let's call it F sub g for force of gravity, is equal to the mass times the acceleration, mass times g, and we'll often use the letter W for that. We call it the weight of the object. So an object in free fall has a force of gravity acting on it. Force of gravity acting on it downward in the amount mg. What if it wasn't in free fall? How about this object here? Does that still have a weight? Yes, it does. How come it isn't accelerating? Evidently, there must be some other force acting that's canceling the force of gravity. We're going to come back and talk about that in a moment. But my point right now is that weight is universal. Everything's got a weight, mg. Whether it's actually falling or not depends on whether there's some other forces acting on the system. I meant to say this when I was talking about the second law, by the way. The second law says F equals ma. What if there are 16 different forces acting on an object, pulling every which way? Then you add them up as vectors, get the total force that's acting on the system. That's what's going to determine the acceleration. It's not that an object has 16 different accelerations, one due to each force. No, that's nonsense. An object only has one acceleration. It's only got one position, one velocity, one acceleration. How do you get it? Add up all the forces first, and that's equal to the mass times the acceleration. So evidently this brick has some other force acting on it in addition to the force of gravity down. It must have a force in the upward direction in the amount mg, exactly canceling the force of gravity acting down. You might start thinking about what that force is that's keeping that brick from going through the table. So every object has a weight, a force of gravity acting on it, mg. By the way, I hope you're aware of the distinction between weight and mass. Weight is a force. It's a force, not a mass. It's measured in newtons, not in kilograms. And the weight of an object depends entirely on where it's located because it's m times g. We say g is equal to 9.8. That's because in Massachusetts, g is approximately 9.8. If you went down to the equator up to the top of Mount Everest, you would get a slightly different value of g. And if you went to the moon, you would get a substantially different value for the acceleration of gravity on the surface of the moon. So the weight of an object depends entirely on where it is, at least within that sense that the acceleration of gravity varies from point to point. The mass of an object is universal. I don't care where you take it, it's still got the same number of protons in it, and its mass is exactly the same wherever it's located, but the weight depends on where it is, and weight is a force, not a mass. Mass is universal. Let's see. Suppose that I took this 1 kilogram mass and hung it on my Newton meter. What should it register? 9.8, isn't that right? If I had a 1 kilogram mass, then the weight of that should be 1 kilogram times g, 9.8 meters per second squared, which is 9.8 newtons. So let's see if it's true. It's better not lie to me now. 9.8. Believe it? Next kind of force that we need to know about. Force is exerted by strings or ropes. We call it tension. string or rope. So let's see. This is a little bit tricky to think about. There's a piece of string, and maybe there's some turkey hanging on to each end of it or something, and we're pulling on it. So it's under tension. This rope is pulling to the right on whoever is holding it on that side. And over here, the same tension pulling to the left on the person who's holding it there. This person is pulling to the right, the rope is pulling back, is pulling to the left, the rope is pulling back to the right. I'm talking about the force exerted by the rope on the people now, not force exerted by the people on the rope, although Newton's third law in that case would tell you exactly that it has to be the same. But I'm talking about the force exerted by the rope on the person. That tension is pulling to the right on this guy and to the left on that guy. And as long as the rope is massless, that tension is the same all the way down the line. If the rope is massive, a heavy rope, and it's accelerating, then the tension is not the same all the way down the line because each little piece of rope has got to be accelerated, F equals ma, so the net tension on any given piece of rope would not be the same on the two ends because the difference between the tension that side and the tension this side would have to be the mass of the rope times the acceleration. But almost always in this course we assume that ropes and strings are blissfully massless. This makes life a whole lot easier, just means that the tension is the same all the way down the line. As long as the rope is massless, how could you measure it, incidentally? One thing that you might do if you wanted to know what is the tension in a rope is you could take one of these little things, slice the rope, cut the rope and attach one of these meters to it. Then this thing would just measure what is the tension in that running. Attach the two ends to the two pieces of this, obviously, and that would be a way of measuring the tension in the rope. So put one of those Newton meters in there that hooks on the two ends, and that would be a way of finding what the tension in the rope is. The important thing, and kind of elusive when you first encounter it, is the fact that the tension pulls to the right on this guy, but it pulls to the left on that guy. If I say in the rope itself, which direction does the tension point? Well, I don't know. It's kind of on any given piece of the rope, it's pulling in both directions, isn't that right? On a little segment of it. So the direction that tension acts, I don't think that that's an answerable question. What you need to do is look at what it's attached to, and then of course it's clear this thing is pulling to the left on this guy and pulling to the right on this guy. But the same tension all the way down the line. By the way, what if the rope goes over a pulley or something like that? Again, assuming that it's a massless rope and a massless, frictionless pulley, later on we'll fix that up to massless rope. Maybe that's sensible. I mean, if you're lifting a 2-ton box or something like that, the fact that the rope would actually be 2 kilograms is going to be irrelevant to the problem. But the pulleys, the mass of the pulley or friction in the pulley might not be irrelevant to the problem. But for the moment, we're going to assume that the pulley is massless and frictionless. Then this rope, even though it goes around a pulley like that, the tension still stays exactly the same. In fact, that's what a pulley does. It changes the direction of the tension without changing its magnitude. Let's run an example or two of that. Okay, I've got hanging from the ceiling a rope, and at the end of that rope there's an object whose mass is m. This here is a massless rope, as you can see. Just look at it, massless. Massless rope, and I ask you the question, what's the tension in that massless rope? You probably know already what the tension in there is, but I want to get you in the habit of being very systematic about handling problems like this. First thing I'm going to do is draw what the books call, for reasons I've never understood, a free body diagram. That means I focus my attention on the object in question, the mass m, and then, using a different colored chalk, I'm going to draw in all of the forces that are acting on that object. What forces can you say act on the mass m?
Tension and weight.
Gravity. Certainly acting downward, W equals mg. What else? Tension, acting upwards. That rope is pulling this thing upward. What else? Good, nothing. That's it. Those are the only forces that are acting on this object. By the way, notice that here, I didn't draw the ceiling in here, I didn't draw the rope, nothing. I just drew the object, the M. What forces act on it? W pulling down, T pulling up. Now I apply Newton's second law of motion, F equals ma. Well, the A is 0 in this case, it's not accelerating. So what must the net force be? 0. Therefore, W acting down minus T acting up is equal to 0, and hence T equals mg. That's the tension in the rope. As I say, that was pretty obvious from the beginning. When you see this thing dangling here from the rope, the tension pulling up has got to exactly balance the force of gravity pulling down. Obviously, the tension is mg. But let's make it a little bit more complicated. I'm going to give you now two objects hanging from here. M1 and M2. Jesus. Okay, I'll just set it up. May not have a chance to do this. I'll draw separately the two objects, free body diagram for M1 and a free body diagram for M2. What I want to know is, of course, what's the tension in that string and the tension in that string. What forces? You tell me what forces act on M1. No, wait a minute. We go till 11, don't we? I got to, okay. For some reason, I was alarmed. My course of non-holy I was routinely running 10 minutes over because I was confusing it with when the clock stops in here. Okay, so 10 minutes, that's good. So, run this clock. M1, what forces act on M1? You tell me.
Gravity.
Gravity acts downward. A good place to start. M1 times G. What else? The force of gravity on M2.
Tension too.
Very good statement. But that obviously has something to do with it. But that's the force on M2. I'm not going to stick that in this diagram because I am drawing right at the moment only forces acting on M1. So I will put that in anticipation. M2 times G, that's a force that acts on this object here. And I know what you're thinking in the back of your mind. Yeah, but obviously that somehow or other pulls down more on M1. I don't know. M1 doesn't know about the existence of M2. What it does know is that there's a string pulling down on it with a tension T2. And what's in the back of your mind is, yeah, but T2, how did that get there in the first place? It got there because there was something hanging on the bottom of it. That's true, but let's not, this stuff is incredibly easy if you don't allow your mind to wander, or if you don't try to jump ahead and anticipate. Right at the moment, I'm just looking at M1. I'm not looking at M2. I don't know about the force of gravity. All I know is that there's a T2 pulling downward on M1, right? What else acts on M1? T1 acting up. How about M2? Force of gravity acting down, of course. What else?
T2.
T2 pulling upward. What else?
That's it.
Good. Nothing else. That's it. Now let's go ahead and apply Newton's second law to each of these objects. Here, F total is not accelerating, so the total force has got to be equal to 0. So T2 equals M2G. Therefore, coming back to this problem over here, I have T1 has got to balance M1G and T2, but T2 is M2G, so there's the tension in that row. And you were dead right. You said M2G, but you were ahead of the game. It wasn't directly M2G. It was that you happen to know that T2 was equal to M2G, but that came from the analysis of the second one. You understand why I'm being fussy about this? If you had a 10 times more complicated problem, your way of doing business would be very slippery, and it's the easiest way to make errors is by anticipating something that you're pretty sure is true, but that really belongs to a different part of the problem. So my advice to you is be stupidly plotting about this stuff. Draw each subsystem, if you like. Here there are 2 subsystems, M1 and M2. On each of those, draw in the forces acting on it and nothing but the forces that are acting on it. Another thing that people often will do is, not in a problem like this, but suppose that somehow there was some acceleration going on here. They will put in acceleration, too, on the same diagram, drawing that in with the same color pen. Very dangerous. I'm just drawing forces. When you draw the free body diagrams here, put the forces and only the forces acting on that object and only that object, and then apply Newton's second law of motion. So, end of that sermon. Where am I? Item 3, third type of force. I come back to the force that keeps that brick from falling through the table. We call them normal forces. The word normal is one of 3 different words for perpendicular that are used in physics. In physics, we call it perpendicular if it's a sort of elementary subject. We call it normal if it's a little more sophisticated. And we call it orthogonal if it's super sophisticated. And they all mean exactly the same thing. They just mean perpendicular. Normal force, normal means perpendicular to the surface. Normal forces act between 2 objects in contact, and they're perpendicular to the surface of contact. So, here's that brick sitting on the table. And it's got a force of gravity acting on it. of course, everything in this room has got a force of gravity acting on it. That force is mg acting downward. In that case, how come the brick isn't accelerating downward? Answer, evidently there must be some other force here acting upward, and that is precisely the normal force. When I first heard this story, I thought it was the most transparent piece of sophistry, because what they're trying to do is rescue Newton's second law of motion. Obviously, the only force on that thing is the force of gravity acting down, and yet it's not accelerating, so somebody concoct some new force, and they call it normal force, and tell me that that cancels the force of gravity. A lot of people, actually, I hope that you aren't affected by this, but a lot of people have the notion that when you put an object on a table like that, well, the table kind of shields or cancels out the force of gravity, so there is no force of gravity acting on this because it's sitting on the table. That's, I mean, it's not stupid, but it's just dead wrong. There is still a force of gravity acting on that thing, pushing it down just as much. But there's another force pushing up, and that's what we call a normal force. How do I know it's there? Because otherwise the damn thing would be accelerating. Sounds like it's a rationalization. Well, I agree, but we're going to come and think about what that force actually is.
Isn't it due to Newton's third law?
No, it is precisely not due to Newton's third law, but I love that question. The man says it's got to be minus mg because of Newton's third law. Why is that reasoning incorrect?
The two forces acting on the same object.
They're both acting on the brick. Newton's third law can't have anything to say about that. Now, there is, of course, a Newton's third law analog to mg. What is that? mg is the force that the Earth exerts on the brick, pulling it down. Newton's third law says there must be a force exerted by the brick on the Earth, pulling it up. Yeah. There it is. The Earth is being pulled up with a force, a measly, from its point of view, measly force, and the mass of that brick times g, pulling up. But that's a force that's acting on the Earth. So if you said, yes, because the Earth is exerting a gravitational force on the brick, therefore the brick must be exerting a gravitational force on the Earth, and that must be in the amount mg, I would agree with you entirely. But none of that had anything to do with n. N is a force exerted by the table on the brick. And I could run the same argument there, too. Okay, there must be a Newton's third law opposite to that. That's right. That's the brick, the force exerted by the brick on the table. That's pushing downward. But I'm not going to draw those into the diagram because this is a force acting on the Earth. And I was just talking about the brick. This is a force acting on the table. And I was just talking about the brick. The forces on the brick are 2, N, and mg. And must be equal to mg, not because of Newton's third law, although, run a test sometime. Ask 5 physics graduate students, and I bet you that 4 of them will say n has to be equal to mg because of Newton's third law, exactly what you were saying. So it's not a bad error, very common error. But Newton's third law got nothing to do with it. What is the nature of that force that pushes up on the brick, and how on earth does the table know to push up just exactly mg? I think of the table as being kind of like a mattress, you know? It's a bunch of springs. And what happens is when you stick a brick on there, it kind of squeezes those 2 springs downward, so they're tighter sprung. When the spring is compressed, it exerts a force in the upward direction. And that's what that N is. If you stick a little bit of extra mass on here, it squeezes those springs down a little bit more. And they exert a larger force in the upward direction. It's automatically self-correcting. How nice. A little bit more force from the top produces automatically a little bit more restoring force. What are those springs? Well, they're the atoms and molecules in the surface.